Good evening, everybody. Today we will just slowly move to the ligand field theory. So, how the ligands around the different metal centers can give rise to a typical field which is completely different from the crystal field. But before proceeding to that particular theory, how we can utilize that theory to explain some of the bonding parameter for the different metal complexes, we will finish the remaining part of the magnetic properties what we are talking about, that because these magnetic properties or magnetic behavior for the different metal complexes are basically supporting our corresponding proposition for crystal field theory, that whatever ligand we have which is surrounding the metal center, and if metal is there as Mn plus, and if we can have say 6 ligands. So, without considering the corresponding bonding parameter between M and the different ligand and the ligand donor atoms, we can talk about the corresponding orbitals which are occupying the different number of unpaired electrons. So, these unpaired electrons are giving rise to very interesting properties for these metal complexes when they are isolated as a mononuclear compound. If they are present in a dinuclear compound, which we will see further again when we will be talking about little these things in terms of the corresponding biological aspects of metal complexes, that in different biological systems we can have several paramagnetic centers, and those paramagnetic centers can bind some other small molecules which are very useful in our system for our living or different living organisms, such as O2 molecule, which itself is also paramagnetic. So, the situation is becoming much more complex when two metal centers are they are having some amount of paramagnetism. It can be 1 electron paramagnetism, or it can be 2 electron or 3 electron paramagnetics, and apart from that the small molecule or small group which is bound to these metal centers are also paramagnetic in nature. So, overall how we can monitor experimentally the corresponding behavior. So, what experiment we basically propose for finding out that particular properties of these centers, showing that individual centers for the individual paramagnetism as well as the overall some interaction, such as in some case it can be antiferromagnetic or in some other cases ferromagnetic. So, we will see that what are the different experimental evidences, how we can measure these magnetic moments, because theoretically already we have seen that there are several techniques what we can use for say different types of interactions, whether we are involving the corresponding mu j equation, mu L equation or mu S equation to determine the corresponding magnetic moments and their orbital contributions also. But right now what we can see that we want to measure the corresponding magnetic susceptibility. So, it is the chi m values which we are going to measure to find the exact number of unpaired electrons which are present in a particular metal complex or any other multinuclear metal complex also. And the paramagnetic substances which are present there, if we place them in a typical magnetic field, they will be attracted. So, how we can measure this amount of attraction between the paramagnetic centers, that means that between this paramagnetic compound and some applied magnetic field, that we will find out. Because all the different other spectroscopic techniques which are depending on magnetic field can also give some idea whether we should be able to measure these particular paramagnetic substances for those spectroscopic signatures like NMR and EPR using those magnetic fields. So, the first thing what we can use is a very simple thing, that is a balance, analytical balance, which is very much sensitive, say up to say fifth place of decimal we can measure. So, that balance we can be converted to a Gauss balance, where we use some permanent magnet, and within the magnetic field we place the corresponding sample and we measure the weight. So, use of this Gauss balance takes the weight change of the sample, that means the change of weight in presence of the magnetic field and in absence of that magnetic field. So, we will use the analytical balance, and the sample is placed in a homogeneous constant magnetic field. So, of a very little bit of high magnetic field value of say 1 Tesla to 10 Tesla, and whatever measurements we make, it can be calibrated against a known standard like mercury cobalt to tetrathiocyanate compound, tetrathiocyanate compound of this cobalt. So, which has a fixed magnetic moment value as well as the corresponding molar magnetic susceptibility, that means the chi-m value. Also we can use copper sulphate pentahydrate also. So, we can use copper sulphate pentahydrate in these two samples. These are very good standards for measuring the mu effective value or mu spin only value, because in this particular case what we know that it has one unpaired electron, and theoretically we can get the corresponding mu effective or mu spin only value for this copper sulphate sample, but also we can have some value for this corresponding molar susceptibility or gram susceptibility values. So, we just simply compare the corresponding chi-g and chi-m values when we take certain amount of this copper sulphate solution, and in a uniform measuring technique, that means we take the corresponding tube which is known as the Gauss tube, and this Gauss tube is there, and which is once it is filled with the standard sample, and we take the two weights, that means one weight in absence of the magnetic field and one in presence of the magnetic field. Similarly, the same tube can be filled with the next time can be filled with the sample. So, this is for standard and this is for the sample itself, and there also we have two weights, the W1, W2, or rather we can consider it as W3 or W4. So, using these four weights W1, W2, W3 and W4, and by knowing the corresponding chi-g values for this copper sulphate, we can determine the corresponding mu effective value or the mu spin only value for the unknown sample what we are going to measure in the solid state in the powder form. So, this particular technique is useful for solid powdered sample. We cannot go for anything which is in solution or some other thing when we measure the corresponding biological samples which are always present in solution. So, for those samples we have to use some other different technique where the sensitivity of the corresponding balance is much more, and we can sense one particular metal center, say if it is hemoglobin or myoglobin, within a very big protein envelope. So, protein chain is there which has a very high molecular weight, several thousand kilodalton, and we have to sense this particular paramagnetism which is trapped inside the macromolecular chain of the protein structure. So, the sensitivity of the corresponding balance should be much more, such that we can sense the corresponding values of the small change in the corresponding chi-g or the chi-m values. So, the standard is very much useful for any other thing, that the standard can be utilized to calibrate the instrument. That means, the same tube where we can go for the corresponding diamagnetic correction for the tube also. For from the known Pascal's constants, we go for the corresponding diamagnetic correction, and we measure ultimately the mu effective and its corrected form. So, it basically measured the Gauss balance. What we can have is used to measure the magnetic susceptibility, that means the chi g, and which when multiplied by the molecular weight we get the corresponding chi m value. It was first invented by Louis Georges Gauss. So, that is why it is named as Gauss balance. It is a very simple technique and very useful technique, where we have the permanent magnet. So, these are the two poles of the permanent magnet, and we place the sample within a tube which is known as the Gauss tube, and magnet, once it is switched on and in another case it is switched off, and this the lower end of a balance which can be a single pan balance which can measure up to 5th place of decimal, which is a very sophisticated magnetic balance and which is encased in a glass shield. And this particular sample which is facing this magnet, it has to be seen that it is extending because the tube is big one. So, that is the only drawback of this particular technique, is that we can use up to say 8 to 9 centimeter of this length, and for that purpose if the tube is not very much big, it is close to that of our NMR or EPR tube, and the magnetic field is extended. This is the maximum possible magnetic field where we are getting at the center of the magnet, and which is extending from 1 to 0. So, this here we do not have this magnetic, any kind of magnetic field. So, this because we have to go for the corresponding integration from a 1 to 0, that means maximum possible magnetic field, to a 0 magnetic field situation, and in that situation we just use to measure the corresponding change in the weight. That is why we require comparatively large amount of sample which has to be filled this tube, and the tube is placed inside the magnetic field. So, we get some attraction and repulsion when we have the diamagnetic sample. The diamagnetic samples get repulsion by the magnetic field, and when we have a metal complex and even it is bound by several such ligand centers, and if the ligands are very big, and is also it can have this several steric crowding, and it can have several other atoms. So, this ligand part is also diamagnetic. So, within a diamagnetic host or diamagnetic envelope, we just simply go for the measurement of this corresponding paramagnetism which is originating from the metal center for the complex. So, for that also one is tube, the tube what we are used for measuring, and two is the ligand part. These two we have to use for the diamagnetic corrections, and for that standard tables are there, and which are Pascal's constants, and those Pascal's constants are used to go for this corresponding corrected chi m and the chi g value to determine the corresponding mu effective value after this correction is known as the mu effective corrected one. So, within the magnetic field, when we place the sample, there will be a change in apparent weight of the sample when the magnetic field is turned on. So, that is the basic principle behind this simple technique of Gauss balance for measuring the paramagnetism of these metal complexes. But what we can use nowadays to see very small magnetic interactions when we have multinuclear metal complexes such as 4 copper centers are present in any sample, or any biological sample such as hemocyanin or any other thing where 2 copper centers are present, and sometimes we have the corresponding ambiguity whether the copper ions present in hemocyanin molecules are paramagnetic or not. That means whether the copper centers present are in +2 oxidation state, which can only be paramagnetic, or in its reduced form, that means the copper 1 plus, because the cuprous state it will be diamagnetic. So, for that very sensitive magnetometer we require, utilizing the superconducting quantum interference technique, quantum interference device. The SQUID is useful for that particular purpose to measure very low magnetic moment value, and when it can be used for any change for the variable temperature measurements, also for knowing the ferromagnetic behavior or anti-ferromagnetic behavior at very low temperatures. So, this is another schematics which basically tells us that how the thing is basically changing. That means, this length is extending from a maximum magnetic field possible to a zero magnetic field, but when it is attracted by the magnetic field, we see there is a change in the weight. That means, the tube goes inside the magnet when the magnet is turned on. So, sample is basically packed nicely, uniform packing is required for this tube, and it is placed in a glass tube, very simple glass tube. Homemade glass blowing section can also do that coil tube for us. And electromagnet, this is not a very sophisticated one, is a permanent electromagnet we need, which is providing the corresponding magnetic field. So, by doing this, we just basically change of weight can be measured using this balance. So, very single pan good balance is required. So, balance from the balance pan we put the hook, one hook, and from that hook basically it is suspended within the magnetic field. So, the next particular balance what we can use is a different one compared to the very simple Gauss balance, which is known as Evans balance. So, in this particular technique the balance is a different one, where we can consider it as a torsion balance, is not a simple single pan balance what we use from certain good companies like Mettler and others, where a single pan balance is very much useful to measure any quantitative determination of weight change up to 4th or 5th place of decimal. So, in this torsion balance, a sample is placed in a fixed position and a variable secondary magnet is utilized to bring the magnet back to its initial position. That means, we just use the corresponding magnetic field, the delta H can be added to the H to bring back the magnet to its original position, and this particular torsion balance is particularly useful for different types of susceptibility balances. So, these balances are known as susceptometers or susceptibility balances, where the technique for this measurement is different from that of our Gauss balance. And third type of the balance what we can have, the corresponding Faraday balance, and here the sample is placed in a magnetic field of constant gradient and the weight is taken on a torsion balance. So, balance utilized is a torsion balance, and the method can also provide on magnetic anisotropy. That means, if the magnet is not behaving uniformly in its three directions, three anisotropic directions like this x, y and z, if the magnetic field is different from one other axis compared to x axis or compared to the y axis, then we can have the corresponding magnetic anisotropy present in the sample, and that anisotropy gives us very important informations related to the corresponding magnetic interactions for the corresponding interactions giving rise to the two paramagnetic centers which are interacting. So, what we do in Faraday balance, the field is completely different because the pole heads are different, which is providing us some inhomogeneous magnetic field. In case of Gauss balance, we have a homogeneous field and uniformly the tube is extending from the center of the magnet to outside of the magnetic field. The pole pieces here in case of this Faraday balance are so created that there is a region in which the product of the field strength and the field gradient is in the z direction is constant. That means, on the upward direction we are not changing the corresponding product of field strength and field gradient. That means, with the change in the distance from the center of the magnet, this particular product in the z direction are not changing, and sample is basically placed in that area only. But in case of Gauss balance, that is changing uniformly as we move from a center of the magnet to outside. So, this homogeneity is created for that reason only, such that the field gradient and the field strength remain constant along the axis where we are taking the corresponding weight in, say, z direction. The force which is being operating, or the sample is experiencing that particular force, is independent of the packing of the sample. That means, in case of Gauss balance, we need some uniform packing of the sample and which is nicely packed. But in this particular case, if we do not pack in a uniform way, there is no harm for the measurement, but it depends only on the total mass of the material which is present in the system. And what are the typical advantages for this method over the Gauss method or the corresponding susceptibility torsion balance method, is that the method is sensitive and highly reproducible. That means, if we have 10 measurements and all the measurements would be pretty close to each other. So, there is no need to take the average of, say, 3 or 4 or 5 measurements. So, this is sensitive and highly reproducible, and it can be applied to also to the single crystals. Since we are talking about the magnetic anisotropy, and if we place the single crystals along the corresponding crystal axis x, y and z, so we can differentiate the corresponding magnetic moment values in different axes, that means mu x, mu y and mu z values, which we can find out if we go for the corresponding measurement using a single crystal. The force here again is measured as a weight change using now again a torsion balance. So, balance is again a torsion balance, but only difference from the torsion balance for the measurement of the susceptibility balances is that the magnet is inhomogeneous, and which is focused for measuring the corresponding magnetic anisotropy. So, if we go for these things, that how we are going to measure the corresponding magnetic moments, and the magnetic moments are very much useful for knowing the corresponding crystal field theory. So, basically all these measurements are basically supporting our crystal field theory, where we have seen that the corresponding number of electrons, if we say a nickel compound in +2 oxidation state or some binuclear nickel compound which is binuclear. So, we can measure in both these two cases the corresponding mu effective values, and here also mu effective values, and we just try to look at how these two paramagnetic centers, obviously these two nickel centers are paramagnetic in nature, because we have 8 electrons giving 2 unpaired electrons in the Eg level, and the corresponding splitting for this nickel in octahedral geometry. These two are also in octahedral geometry, and in biological samples it is also present like this in ureases. So, in urease molecule we find the 2 nickel centers are there, which is responsible for urea hydrolysis. Urea is nothing but this. So, this is getting hydrolyzed. So, that can be studied when 2 nickel centers are in close proximity at a distance of, say, 3 angstrom, which is basically binding the urea molecule, and that urea molecule is undergoing the hydrolysis through some nucleophilic attack by HO minus or H2O. So, nucleophilic attack of HO minus or H2O can lead to the hydrolysis reaction. But all these catalytic reactions what we are talking about is taking place on these two nickel substrates. So, it is basically this is the platform, and on that platform the urea is coming and binding to these centers. But if we talk in terms of the corresponding mu effective values for these two centers, whether these two centers are ferromagnetically interacting or anti-ferromagnetic interacting, or that can have some effect on the hydrolytic potential of the urea molecule for the different ureases, that we can see that simply by looking at the corresponding crystal field theory without knowing the bonding parameters, how these bonds are forming and what are the corresponding nature of the corresponding metal ligand bonds, we can talk in terms of the number of unpaired electrons present on the nickel center and how the two unpaired electron from the first nickel center, which we can also consider as nickel A, and the nickel B, the second one, and how they are interacting, that can also be very nicely explained or determined in terms of the corresponding crystal field theory, because this theory tells us that we are not focusing much attention on the ligand charges or the point charges or the different dipoles which are surrounding these particular metal centers. So, we are not talking anything related to the corresponding nature of this bonding with this nickel center for the different ligand donor atoms. So, crystal field theory therefore only focusing our attention or taking us to consider these ligands as only to point charge or the dipole only, and does not take into account of the overlap of the ligand and the metal orbital. So, these are basically the limitation of the crystal field theory, where we are not considering any kind of overlap of ligand and metal orbitals. So, that basically gives us some idea that when we talk these in terms of the crystal field theory and considering the ligands as point charge or the dipole only, what we see that we are not considering any kind of overlap between the metal and the ligand orbitals. So, if we have two centers such as this two can be nickel 2 or copper 2. So, when these are bound, so in this particular case, in case of urease, it is bound by a carbamate unit. So, if we consider that we have two unpaired electron on the first copper and two other on the second copper, and if we think of the interaction which can be say ferromagnetic, that means we are adding off the magnetic moment from one copper center to the other, but we should have something to consider also, that interaction of these ligand orbitals to the metal orbitals, that we are neglecting in case of crystal field theory. So, if the super exchange is taking place through the bridging ligand for this corresponding magnetic behavior, whether it is ferromagnetic in nature or anti-ferromagnetic in nature, we should consider the overlap of the orbitals of M and L. So, we should consider the overlap, but which we are not getting from the crystal field theory. That is why this is the typical limitation of the crystal field theory, and we should modify this particular theory for considering this particular overlap. And also, when we fail to explain the nature of the carbon monoxide ligand, as we see in the spectrochemical series, that carbon monoxide is a stronger ligand than cyanide ion in several such complexes, that when we consider the nickel tetracarbonyl, iron pentacarbonyl or chromium hexacarbonyl, we in all these cases we see that carbon monoxide is behaving as a very strong ligand compared to its Cn minus analog, and these complexes having metal in low oxidation states. So, in several of these complexes where the oxidation state of the metal is 0 or in the low oxidation state, we are unable to explain in terms of the crystal field theory why CO is stronger than Cn minus, which is a neutral ligand. So, that also compel us to consider that there is certain amount of overlap between the carbon monoxide orbitals. That means the formation of the corresponding carbon monoxide molecular orbitals we should have, and these carbon monoxide molecular orbitals will interact with the ligand d orbitals to give us some good information about the metal and ligand overlap. So, we propose the theory which is termed as the ligand field theory, which basically all the time will be utilizing the corresponding molecular orbital approach as we see for the simple molecule. And this approach, what we see that if we just consider that our ligand is carbon monoxide, that means the carbon monoxide is forming from carbon and oxygen. So, instead of considering the carbon monoxide as a point charge or dipole, we will consider the corresponding molecular orbitals of the carbon monoxide. And these carbon monoxide ligands we can use as utilizing their hybrid orbitals or the pure s orbital, which are pointing towards the metal to form the corresponding sigma bonds to the metal. So, today we just simply start our discussion by considering that only sigma bonds are forming between metal and ligand, where the theory can be considered as a ligand field theory, which is basically a admixture of molecular orbitals of the ligand and the corresponding pure orbitals or hybrid orbitals of the metal center, giving rise to the different orientation of the different bonding as well as antibonding orbitals. So, arrangement of these orbitals in different energies and their corresponding occupancy for the unpaired electrons will tell us the corresponding theory as the ligand field theory. And what we have ignored in crystal field theory, that the nature of the ligand, slowly we will just go towards this theory that now we have to consider the nature of the ligand, whether the ligand is carbon monoxide or Cn minus or N3 minus or SCN minus. So, they all have different types of hybrid orbitals available for donation to the metal center. Since we have ignored this nature of this ligand, we are unable to explain in terms of crystal field theory the corresponding spectrochemical series. That means why some ligands are in the strong field ligands and whether others are weak field ligands, though the interaction is not purely electrostatic in nature. So, we just use the typical molecular orbital theory, what we know so far for simple molecules, simple covalent molecules like carbon monoxide, like cyanide, like thiocyanate, like azide, will utilize that molecular orbital theory for the getting the corresponding LFT or ligand field theory. Now, we have the different valence orbitals on the metal and ligand are used to form the different salks. Salks are nothing but symmetry adapted linear combinations. So, we have now the different salks. So, this is nothing but we are now talking with the symmetry, which is very important. That means whether we are talking a corresponding metal complex. So, that is why we are talking so much about the symmetry of the metal complex, whether it is tetrahedral, whether it is octahedral or square pyramidal or trigonal bipyramidal. So, those symmetries are very important because those symmetries will dictate that corresponding adaptation. So, it is symmetry adapted linear, the combination is only linear combinations. So, symmetry adapted linear combinations of the different orbitals. So, if we have those orbitals, so symmetry will dictate a particular type of linear combination, and that combination will give us, these are our new molecular orbitals for the complex. So, if they are coming out from the ligands, we have symmetry adapted linear combinations of those orbitals coming from the ligands, and also from the metal center we are having large number of other orbitals, say s orbital, p orbital and the d orbitals. So, these s, p and d orbitals can form also some amount of symmetry related molecular orbitals for good overlap with the ligand orbitals. So, we will be utilizing these valence orbitals as the different salks, and then we will utilize the preliminary energy level diagram and overlap consideration for knowing the relative energies of the molecular orbitals for their estimated form. That means, whether the energy is higher or lower, that we will just simply guess from these combinations. That means, whatever we are getting, whether we are getting some as bonding orbital or some as the corresponding anti-bonding orbitals. So, two types of bonding we will consider in this particular theory. One is the typical sigma bonding, which is sometimes very close to that of our crystal field theory, when these interactions was purely electrostatic, but now we will have direct overlap between the metal and the ligand orbitals, and if there is a head on overlap, we will be talking in terms of the corresponding delta sigma bonding, and the ligand has a single valence orbital. So, if we have some sigma bonding orbitals available on the metal center, so ligands will have some symmetry related combinations of the different orbitals available on the ligand, or sometimes the pure orbital, say p orbital, the p orbital which can be considered as its valence orbital and which is directed towards the central metal atom to give us the corresponding overlap for sigma bonding. Similarly, what can happen for our pi bonding also? So, we will get the typical pi bonding also, because this pi bonding can now modify the corresponding nature of this metal ligand interaction differently. So, that is why we are getting this information that why carbon monoxide is a stronger ligand than cyanide. So, when the ligand has a field orbital of pi symmetry, which is important, so far we are not considering anything related to that, the ligand field orbital of pi symmetry we are not considering. So, if it has a field orbital of pi symmetry around the ml axis, so those electron density can be donated to the metal, and we can have the corresponding metal ligand pi bond. So, not only sigma bond, which can be considered as a single bond, we can have a multiple bonding between the metal and ligand to give rise to some kind of pi bonding also, like the formation of ethylene and acetylene. That means, multiple bond is also permissible for this system, where we can have both sigma as well as pi bond. So, these are the two pictorial representations which typically tells us that how sigma bonding can take place, where the metal orbital, which is the typical d z square orbital having two lobes directing towards the z axis, along the z axis. So, if the ligands are approaching along the z axis, we find head on overlap between the metal d z square orbital and the ligand p z orbital. So, these are the ligand p z orbitals. These ligand p z orbitals are also facing the z direction. So, that is why we will have good overlap with the ligand p z orbitals with that of the metal d z square orbital. So, the metal d z square orbital, which we have seen in case of the corresponding magnetic moment and the spectroscopic term, that they are basically sometimes they are not contributing much towards the corresponding magnetic moment, but when we are considering the corresponding sigma bond, they have the typical sigma symmetry. That means, the orbitals, the EG set of orbitals in OH symmetry have the matching sigma symmetry with respect to the overlap with the pz orbitals of the ligand. So, if we have ligand along the z axis for an octahedral symmetry. So, along this direction we will have two ligands. So, these two ligands will nicely overlap with the metal dz square orbitals to give us sigma bonds. Similarly, the x square minus y square orbital also coming from the same Eg level of the metal center in OH symmetry. So, these two orbitals are also nicely giving us the corresponding sigma overlap. So, when they are in x square minus y square symmetry, so they also go for some head on overlap with the ligands coming from x and y direction. So, these two orbitals are well matched for giving us the corresponding sigma symmetry for the formation of the sigma bonds to the metal complex in octahedral symmetry. So, utilizing this Ligand field theory, we describe the bonding, the orbital arrangement, that means how many of them are bonding orbitals and how many they are antibonding orbitals, and what are the corresponding separation between these orbitals, and whether those are matching for the corresponding spectrochemical series that can be obtained from this theory, which are therefore characteristic, that the bonding parameter and the orbital arrangement thing, which are characteristic for all the different types of coordination complexes. And now, if we arrange 6 ligands around the metal complex in octahedral geometry, we will have 6 sigma bonds facing 2 each from the 3 axes x, y and z. So, the 6 sigma donor ligands, how they are forming, because the molecular orbitals will be formed by coordination result from the donation of 2 electrons by each of the 6 sigma donor ligands. So, if we have 6 sigma donor ligands along the 6 axis of the octahedron to the d orbitals on the metal ion, we find that in case of octahedral complexes, the ligands will approach along x and y and z axis, and the sigma symmetry orbitals form bonding and antibonding combinations with the dz square and dx square minus y square orbitals only, because these two orbitals are only pointing towards the 3 axis. So, if the combination is there for sigma symmetry, we will have sigma bonding as well as sigma star, which can be considered as the antibonding level. So, these two orbitals will be utilized for the sigma bonding for these metal complexes in OH symmetry. But what about the T2G set? The T2G sets of orbitals, that means the dxy, dxz and dayz orbitals, will remain as non-bonding orbitals, because they are not facing directly to the ligand systems, that means the ligand orbitals. So, they will not have any interaction with the ligand orbitals, and some weak bonding or antibonding interactions can take place with the s and p orbitals of the metal ion, and we will have a total of 6 bonding and 6 antibonding molecular orbitals. So, we will have non-bonding orbitals, and then we can have the corresponding involving the s and p orbitals. So, we will have 1s 3p. So, 4 orbitals and plus 5 of the d orbitals. So, all these d orbitals can give rise to the corresponding 6 bonding and 6 antibonding molecular orbitals for the system. So, what we get, that 6 ligand donor orbitals collectively form a reducible representation. So, since we are talking the corresponding symmetry level, so for getting all these things we have to utilize the corresponding character table for the symmetry level of the different orbitals. So, if we just utilize the corresponding character table for octahedral symmetry, we will have the typical reducible representation. So, we all know from the this corresponding thing that what we get for this particular arrangement, that if we get the corresponding character table for octahedral symmetry, the reducible representation of this octahedral symmetry we can get, and from that reducible representation we can have the corresponding irreducible format, that means irreducible representation, and those irreducible representations have some symmetry level, and from those symmetry levels we will take out the corresponding orbitals for the matched one. So, the 6 Ligand sigma orbitals, the p orbitals or the hybrid orbitals with the same symmetry can match, that means the 6 salks from the ligand. So, either s and p orbitals or the hybrid orbitals from those ligands we can match the symmetries of s, px, py, pz and 3 dz square and 3 dx square minus y square metal orbitals. So, matching will be with all the orbitals. So, now we will find slowly that whatever we are discussing for crystal field theory, we are just talking in terms of the corresponding d orbitals only, but now we see that s and p orbitals can also show some contribution for the formation of these molecular orbitals. So, the combination of the ligand and metal orbitals forming 6 bonding and 6 anti-bonding orbitals with A1G, EG and T1U symmetries. So, these are the 3 irreducible representations which will be coming out from the corresponding reducible representations for the corresponding character table, and these are the corresponding sets which are the corresponding symmetry level for those orbitals. So, 6 bonding orbitals are filled by electrons donated by the ligands. So, whatever bonding orbitals we will have, so those bonding orbitals will be occupied by the ligand electrons which are donated to the metal centers. So, the metal T2G orbitals, so these are the corresponding A1G, EG and T1U set, but the T2G orbitals which we all know that the T2G set and the EG set, so this is the corresponding spectroscopic level and the orbitals will be labeled in the small lowercase T2G. For these orbitals do not have appropriate symmetry, that is why we are talking that these 2 orbitals are remaining as the corresponding non-bonding orbitals. So, the molecular symmetry terms, the 6 lone pair orbitals form the ligands, one from each form the 6 symmetry adapted linear combinations that we have just now discussed, and also sometimes we are considering these as ligand group orbitals. So, if the ligand is providing 6 such groups of orbitals, and the combination of those will be considered as the ligand group orbitals or salks. So, these are the corresponding irreducible representations. From the reducible representations, the gamma read it can be represented as the corresponding irreducible representation, and these basically span these 3 symmetry levels A1G, T1U and EG. So, our orbitals, the salks or LGOs will have these symmetry levels for the molecular orbital formation. So, this is the reducible representation for the octahedral symmetry, and these are the all possible symmetry operations and their contributions for the reducible representations, and there are several useful techniques for getting the corresponding irreducible representations from the reducible representation for any such table for this representation. So, this reducible representation will reduce into A1G, EG and T1U. So, this gamma sigma will give us these 3 levels, and we will now locate these 3 types of symmetry levels for those orbitals for the different sets of orbitals which are coming from the symmetry levels. So, if we have the metal s orbital which is symmetric and the 6 ligands are approaching along the 6th axis, and along these 6 axes we have the corresponding symmetry which is spherically symmetric. So, this we can label as a A1G symmetry, and this A1G symmetry which can match very well if we can put the ligand also. The green balls are the corresponding ligand orbitals, either they are the hybridized orbitals or the pure p orbitals, the lobes from the pure p orbitals. So, they are basically overlapping with this which is a spherically symmetric arrangement. So, we have the matched ligand orbitals with the matched metal orbital with A1G symmetry. So, A1G group orbitals, so these we will call at the ligand group orbitals, the LGOs or the SALCs. So, A1G group orbitals have the same symmetry as an s orbital on the central metal. So, if the central metal ion has the symmetry of A1G, then the ligand group orbital will definitely overlap with the A1G symmetry of the metal orbital. So, that gives us for the first time that it is completely opposite for that what we are talking in terms of the crystal field theory, that here we are just considering the symmetry level as A1G, and s orbital is also coming into the picture for this typical hybridization, and this s orbital can also have some overlap with the ligand orbitals of same symmetry. So, the metal also has 6 valence orbital, this is spanning this irreducible representation, and the s orbital is labeled as A1G, and the set of 3 p orbitals on the metal is labeled as T1u, and dz square and dx square can be labeled as Eg. So, these are the corresponding symmetry level for all the orbitals which are coming for the metal. We will take out of 5 d orbitals, we will take only the 2 d orbitals, the Eg set of d orbitals, 3 p orbitals and the s orbitals. So, 3 plus 2 5 plus 1 6. So, these are the 6 orbitals from the metal side which will be forming the corresponding molecular orbitals to go for the overlap with the corresponding ligand orbitals, and they are nicely matching with the T1u set as p orbitals and Eg set for the dz square and dx square y square orbitals. What we have discussed in detail that these two types of orbitals are only utilized for sigma bond formation with the ligands. So, in octahedral complexes, therefore, the ligands approach along the x, y and z axis. So, their sigma symmetry is matching with the dz square and dx square minus y square orbitals, and they are therefore forming bonding and antibonding combinations related to these dz square and dx square minus y square orbitals from the 5 d orbitals. So, now the ligand will also provide this particular level, that what we have shown just now, that the ligands which are approaching from the z direction. So, these two are basically overlapping with the dz square orbital where the ligand is directing along the z direction. Similarly, dx square minus y square orbital from the metal is overlapping with the 4 ligand orbitals along the x and y axis. So, these two orbitals, the dz square and dx square minus y square, can be labeled as the Eg set from the metal side. Similarly, the other two combinations, that means the combinations of these p orbitals from the ligand set, this is the corresponding combination from the ligand side. So, this is the corresponding combination in terms of ligand group orbitals, and these are another combination of ligand group orbitals having Eg symmetry. So, what we will find, this Eg group of orbitals have the same symmetry therefore as the dz square and dx square minus y square on the central metal. So, we will see good combination for these two sets of orbitals from the metal side as well as from the ligand side, and therefore, E is representation for the doubly degenerate level, what we all know from the crystal field regime also, that we have the Eg set of orbitals are these two, and now this is the doubly degenerate set. So, Eg level, that means the Eg in terms of the corresponding molecular orbitals, what we will write now on the molecular orbital energy level diagram, that this E level will consider as the doubly degenerate level. The T1u group of orbital next have the symmetry as the p orbitals on the central metal, and T therefore represents a triply degenerate level like the doubly degenerate. So, we have s orbital from the metal, we have the corresponding d orbitals, 2 d orbitals from the metal center, now the p orbitals. So, this T1U set what we are getting, these are basically the corresponding Px, Py and Pz orbitals, and these Px, Py and Pz orbitals from the metal side, what we are getting is that this is from the metal side and this is from the ligand side. So, when we have in the metal side these orbitals are these two, and therefore, the ligands are also providing the corresponding ends along the x axis, along the y axis and along the z axis, which are also matching with that of our T1U set of orbitals. So, these 3 p orbitals giving rise in these directions are basically the set of orbitals which are matching with the metal orbitals, and these ligand group orbitals are useful from this T1U symmetry, and those T1U symmetry level is the corresponding orbitals also from the metal as p orbitals and p orbitals from the ligands, and they are utilized for the overlap, and these T1U set of orbitals will find in the molecular orbital for good overlap. So, in our next class we will find how these will just go for these overlap and these interactions. Thank you very much.